Will you please make her very, very, very welcome, Naomi McClure Griffiths.
Thank you very much. I know that it's very easy to get a round of applause out of you, though, because I've just been sitting here for the past 10 minutes. See? There we go. So easy. I don't have to do anything. Okay, so while Chris said that I work on the Square Kilometre Array, which is the next big radio telescope, I'm not going to tell you much about the Square Kilometre Array today, but I will tomorrow. Today, I'm going to tell you about the Milky Way, which is fairly big, so I think it satisfies these requirements. Thank you. So, what I use to explore the Milky Way is this beautiful telescope up here, the Parkes telescope. Anybody been to Parkes? Wow, fantastic. That's a big showing. For those who haven't been to Parkes, this is a 64-meter radio telescope. So in radio astronomy, we get to play with pretty big toys, and this is a nice big toy, but I hope to be playing with even bigger toys in the future. So I'm going to tell you about the Milky Way. The basic outline is that I'm going to tell you about what there is in the Milky Way. Stars a little bit, galaxies, what they are. If you know all that already, you can have a snooze at the beginning, wake up towards the end when it would be more interesting. And then talk about what the Milky Way looks like, which is my basic field of research, is to try to understand what our neighborhood looks like. We live here in this galaxy, and we don't know what it looks like. And in particular, the gas in the galaxy. So stars make up most of the galaxy, but I don't care about stars. I like gas. That's the tiny little bits that's in between the stars, and I'm going to tell you about that and what that tells us about the Milky Way. So when you look out into space with a telescope, you see something like this, a bunch of stars. They're basically dots. They have dots that are different colors, and the different colors are why? Heat, temperature. Temperature is the main thing that determines their, but age is also related in there. So mainly it's the temperature that gives the different colors for the stars. Now there's billions and billions of stars in the galaxy, and they look fantastic, and they have temperatures that range anywhere from 3,000 degrees to 30,000 degrees. Big, big, big range of temperatures. And you put a whole bunch of stars together, and you get something that looks like this. You get a galaxy. Now I'm picking, of course, the most beautiful images that you can choose of galaxies, but that's okay. So this is M51, the Whirlpool Galaxy. And where you see all of these red stars are these old stars along the outsides of spiral arms. So most spiral-type galaxies look like this. They're whirlpools. They have a central bright region and then these arms that come spinning out like a pinwheel. And you can see along these spiral arms are these brown regions, and that's the dust that's in the galaxy. And the dust blocks the light from the stars, and so we see it as a sort of black area there. And there's billions of stars in galaxies. So as we look out into the universe and we look at something like the deep fields of the sky, yeah? Yeah, so there's a lot of stars. This is the main things that you can see there. So the reason it looks so bright is that there's a lot of stars there. But also in the center of many galaxies, most galaxies have a black hole. So they have some size black hole, which is somewhere between 1,000,000 times the mass of the sun and 1,000,000,000 times the mass of the sun, which is in the center, and the stars are orbiting around that. But the reason it looks bright is because there's a lot of stars. And in fact, I'll show you what the center of our own Milky Way looks like a little bit later on, and we can see how many stars and what they do as they orbit around the black hole. So as we look out into space, we see something like this. Now, in a galaxy, there may be anywhere between 10 million and 100 trillion stars. So each one of these little blobby things that we see here that doesn't have a spike on it is a galaxy. And there's tiny ones, they only have a few stars, 10 million, and there's big ones, they have 100 trillion stars. And they can be in size anywhere from 3,000 light years to 300,000 light years in size. Quite a big range of sizes there. And there are more than about 125 billion galaxies in the universe, is the estimate that we have of that. But right up close in front of us, we're lucky to have a galaxy that we can see every night, and that's the Milky Way. So we live in a galaxy, and it's quite a nice-looking galaxy, if I do say so myself. So this is an image of the southern sky. If you were to stand looking up, the south celestial pole is here, so that's what's straight overhead at the South Pole. And the celestial equator is around the side here. So this is like a globe, the southern half of the globe, where the globe is the sky. And you can see this beautiful band of stars that stretches across here, which is the Milky Way. And you can see this every night in the southern hemisphere if you're not in Sydney. And if you're in Sydney, you see kind of a little bit of that. If you go to the north, it's not nearly so spectacular. And the reason is that from the southern hemisphere, the center of the Milky Way, which is this bit here, goes directly overhead. So at some of our southern telescopes, the Milky Way Centre goes right overhead, and we can see it beautifully. Yep?
Why is the Milky Way the shape it is?
Well, so the main part of it is it's shaped basically like a compact disc or a DVD, right? Do you mean how did it come to be that shape, or how did it come to be spiral, or how come it looks like that? All of the above. That alone would be an entire talk, which is a fantastic question. So it's shaped like a compact disc. I would demonstrate, or I'd throw this thing away, basically because of conservation of angular momentum. So it was a spinning blob of stars and gas, which spun, and flattened out into a disk. And most spiral-type galaxies flatten out into disks like that. So that's what gives them a kind of flattened-out disk-like shape. The reason it looks like this is because if you imagine sitting as a little tiny speck of dust on that compact disk or DVD and looking along it, you would see the edge of that disk showing up along here. So that's why you get a little thin band there. So the dimensions are very much like a DVD. It's very, very thin and quite big. And in fact, I think I'll give you all the dimensions in just a second. Yeah. That one there. Sorry. You. Yes.
How fast does the Milky Way Galaxy rotate?
It rotates at about 250 kilometers per second. So reasonably fast. Ooh, okay, yes. So there was one there, and then I'll take that one over there, and then I'll move on, and then I'll get some more questions. Okay?
What does this dust have in the galaxy?
What is the dust?
Yeah, in the galaxy.
Yeah, so the dust in the galaxy is basically big molecules. It's not like the stuff that's underneath our beds. It's not, big, hairy bits of fluff or whatever. It's just large molecules. Some of the really common ones are called polycyclic aromatic hydrocarbons. And there's various other different types of big molecules that form there. There was one over there. So, yep.
So what about irregular galaxies? So why are they so?
Why are they irregular? Very good question. Don't know, actually. Somebody might know, but I don't know. And the reason I don't know is because I spend most of my time with my head in our own galaxy, which is fairly regular in shape.
Maybe I should point out at this point that this could go on all night.
I like it.
But they are very keen with the questions.
That's.
If you want to push on, feel free.
I like the questions. The questions are very good, but I do want to show you some beautiful pictures, if nothing else, during the course of the afternoon. So, okay, one more there, and then I'll push on, and that'll answer a few questions. Yep. Where does the dust come from? It comes from stars themselves. So as stars live their lives, and when they reach towards the end part of their life, they form sort of a dusty shell in them. So they cool down and their outer edges blow out. They cool down and the gas starts to form big molecules together. And that dust gets blown off of the stars and then distributed around. Dust can also just form off of molecules that are sort of hanging around in very cold, dense regions of the galaxy. I'll talk a little bit more about dust and gas in just a couple of minutes. So instead of showing a beautiful picture of a few galaxies, I'll just skip through that because it's more interesting to talk about things that will lead to questions. So this is what we think the Milky Way looks like. This is an artist's impression. Well, the problem with studying the Milky Way is that we do live inside it. It's both a blessing and a curse, because the blessing is that it's very close and we can see things in more detail than we can anywhere else in the universe. So that's a wonderful part of it. The downside is it's like trying to figure out how big the forest is and where all the trees are when you're sitting right in the middle and you can't move around. So you have a very, very limited view of it. We can't fly up above the Milky Way and take a picture of what it looks like if we were looking down on it. But we can put together bits and pieces of evidence that we have about where certain stars are, where certain dense regions of the galaxy are, put that all together and come up with a rough idea of what we think the Milky Way looks like. And this is what we think it looks like. So we think it's a barred spiral galaxy. So it has a long sort of irregular shaped ellipse of stars, which forms this bar here, and then coming off of it are at least two major spiral arms, which we can see here as these two big ones, and then two minor spiral arms, which are not as bright, don't have as many stars. There's a black hole in the center, and I'll tell you about that in a little while. And all the way along the spiral arms are where the very big, very massive stars live. So that's where the stars that are living fast and dying young are. They're formed in the spiral arms. They live most of their life in the spiral arm, and then they die out in fantastic supernova explosions. And all the rest of the stars, which makes up a lot of the stars, are sort of scattered about fairly uniformly because they have lived for, like the sun, 11, 12 billion years. So they're long-lived stars that carry on across there. Okay. So what about some sizes for the Milky Way? So the Milky Way, the distance, so I should have said that we live about here in the Milky Way, somewhere out in kind of the suburbs. It's sort of Penrith kind of area. And that's about 24,000 light years away from the center of the galaxy. And it's a pretty, no offense to anybody who's from Penrith, it's a fairly dull place out here. There's not a lot going on. There are no major spiral arms. There's stars around us, of course, but it's not the most dramatic place in the galaxy. And the Milky Way is a barred spiral, as I said. It's part of an area called the local group of galaxies. And galaxies tend to like to hang out together. They're sort of like high school students. They go around in groups. There's usually one or two who are the noisiest. And then there's a few who are not quite as noisy, who kind of just get on with their business. And the local group of galaxies is sort of like that. So the Milky Way is one of the noisy galaxies. It's a big, large spiral. Yep. Yes?
So how scientists measure the size of galaxies?
How do we measure the size of galaxies? Yeah, that's a really good question. So there's a lot of different ways that we can do it. The best way is to measure the parallax of objects. So what we do is we look for that object to sort of move a little bit as the sun goes around, as the Earth goes around the sun. I'm sure I've got that right. I should know that one, shouldn't I? So as the Earth goes around the sun, we see an object move a little bit, and we can tell exactly how far away it is. That's the best way to get distances, and we can then estimate if we can see how bright something is, and we know how bright it should be, and we measure its parallax. We can start to figure out where things are in the galaxy. So that's been used quite a lot to understand the size of the Milky Way. For other galaxies, we use things like Cepheid variables. They're types of stars that vary, and you can, by their period, you know how bright they should be. You see how bright they are, and that tells you how far away they are. But that's one of the biggest problems in astronomy, because it is fundamentally a two-dimensional science. We look up at the sky, and we see everything projected onto the celestial sphere. And the big key is to figure out how far away things are and to put together the three-dimensional picture. And that's not always an easy thing to do. Yes?
So how about the thickness of the galaxy?
Yep. Thickness is that slide there. So it's about 1,000 light years thick in its stars, and you compare that with 100,000 light years across in size. So 1,000 light years thick, 100,000 light years across in its size. That's the stars. Now, I'm going to talk a lot more about the gas in the galaxy, which acts quite differently from the stars, and it's much thicker than the stars, about a factor of 10 thicker than the stars in its thickness. So the total mass of the galaxy is about 1,000 billion times the mass of the sun. So it's a hefty sort of thing out there. So the galaxy, if we could see it fully on its side and compare it with other galaxies, it probably would look something like this. So this is the M104 Sombrero galaxy. So the disk of the galaxy is this part here. And you can see there are stars all the way around it in a perfect sphere. Those are very old halo-type stars. Yeah? Aha! So the best way for measuring the mass of galaxies is to measure the rotational velocity of objects. So objects, we can measure their velocity, and they're rotating about the center of the galaxy. We can then apply our basic physics, our high school physics, and estimate how much mass is inside whatever orbit that is, and that gives us an estimate of the mass. But if you do that and you compare all the stars, so you add up the light, right? You add up the light that's inside a certain area and you add up the velocities, you find that when you get out to the edges of the galaxy, the velocities aren't dropping off. So there's still mass accumulating there, but the stars are all gone, and that's dark matter. So that's how we find that there. Okay, I don't know who was first there, so
Very quickly.
yeah.
Is that image real, like optically real, false color, or artificial?
So that is a real image. It's probably false color because most images are false color, but I'm not sure because I got this one from the European Space Agency website. But it is a real image taken from the real telescope of another galaxy.
Very cool.
Yep. Okay, there was one there, one, then one there.
So is the galaxy expanding or
So our galaxy is probably not expanding significantly. In fact, one of the things that I'll talk about is how do we keep it basically as big as it is. Of course, space is expanding itself, but the galaxy is probably not getting much bigger. Other galaxies, some are in their sort of early formation stages. As you look back into the universe, you see galaxies that are still forming. They're getting bigger all the time, and other ones are becoming dead, basically. Yes?
Yeah, how do you determine the lifetime of a star? What affects it?
Yeah, okay. Ooh, this takes me back to my physics undergraduate. So you can tell, so stars have a certain amount of gas in them, right? And they fuse that gas. So you take, say it's a big bowl of hydrogen, it's going to fuse that gas. At some point, it's going to run out of hydrogen to fuse. And then it starts fusing the next things along and the higher elements along, carbon, nitrogen, oxygen, and then it runs out of that. So you can do basic calculations of the lifetime of a star just on how much mass there is how much they can burn up. But they do it much faster. There's a much higher rate of converting mass if they're a bigger star. And so there's a lot of factors that come in there. But there's really good relationships that have been studied really carefully as to what the lifetimes are for stars of certain masses. Okay, one more and then I'll move on, then we'll do some more. Yep? Because it was the Via Lactea. So because it looks like a milky band of stars, it's the part of the sky where it's black and then it's sort of white and it looks maybe like you poured a bunch of milk through the sky. I mean, not exactly like that, but that's the rough basic idea behind it. Okay, so what's in the Milky Way? 96% of visible matter are stars. I say visible matter because, of course, most matter is not visible, right? 90% is dark matter, 10% is the stars and gas. And of that 10%, 96% of the visible matter is stars, and 4% of that, 4% of the visible matter is gas and dust. And that's the fun stuff, the gas and dust. Why is it the fun stuff? Well, these are bright dots. I mean, that's basically what they are. They're bright dots. But the gas and the dust gives you ideas of dynamics. It tells you how things move around. And it's from the gas and dust that stars are formed. And it's to the gas and dust that they return when they die. So it's sort of like the soil, the base place where everything starts from, has to start from the gas and dust. So interstellar gas has lots and lots of beautiful pictures that you've probably seen. This is an HST image of dust pillars in the Eagle Nebula. So these are these very big molecules that block out the light from the stars coming behind them. You can see some stars here and these big black things here. And they've got incredible structures along them. So this is an image taken in visible light where you're seeing obscuration. Yeah?
Why do they form those particular structures as opposed to it's like a blank?
There's a PhD in that, if you can answer that question. We don't know. There's lots of different things that do cause structures to form in various different ways. So just like when you look out at the clouds in the sky, and you see, you know, one of them looks like a teddy bear, and one of them looks like sort of sheets, those form different structures because of the motions of the air around them, because of instabilities that happen in that. In the gas in the galaxy, there are magnetic fields which constrain gas and pull it in different ways. Lots of different effects that change the structures. And in fact, I'm writing a research proposal, you know, in the airport on the way here, which is about exactly that question. Yes?
Do they change shape?
Yes, they do, but not in our lifetime, sadly. If you could hang around for like, you know, a few 100,000 years, then yes, but not. It's a slow process. Everything in the universe is very, very slow, really. Not everything, but most things.
Quick question, and I'm going to jump in because I can. What's that scale?
This is very small. This is sub-parsec, so this is probably less than a light year in scale, but I can't remember the exact scaling.
Still big.
Well, okay, yeah, that's still...
On an astronomical scale, it's small.
It's small on an astronomical scale. On a scale like compared with Earth, yes, it's still big. Yeah. Yes. Okay, there was one question there.
We can't see how it moves within a lifetime or within 1,000 years. How do you know if they change at all?
Aha, well, I can actually see that they move, and I'll tell you how in just a few minutes. There's only some things we can't tell, but some things we can tell. So I'll show you. If I haven't answered the question in about 8 minutes, ask it again. Okay, yes, there.
If this gas and dust that you're saying blocks out light and forms a large part of our galaxy, how can our telescope see through them? The galaxy?
I'll answer that question in just a couple of minutes, too. Okay, so that tells me I should move on, because I've got 2 questions in a row that I'm going to answer. So the question about how we can see through is the next one. So the image that I just showed you before from HST is an optical telescope. That's visible light. It's like what we see with our eyes. But the electromagnetic spectrum is a lot more interesting than just what we can see with our eyes. We have a very, very limited range. We're kind of, you know, simple creatures. So you probably have all seen, like, you know, an infrared image of yourselves. You walk through an airport scanner, and it's looking to see if you've got Ebola or something like that. And you get scanned, and you see that, geez, my forehead is hot. I hope they don't pick me up. That's infrared. That's another part of the electromagnetic spectrum. But there are a lot of different parts of the electromagnetic spectrum. They range from gamma rays, X-rays, you know, take a picture of your bones, ultraviolet, get a sunburn. What we can see with our eyes in the visible infrared, which we tend to think of as looking at heat. Microwaves, like heating up your food and using your various devices, and radio waves. And they have different wavelengths. So the wavelengths that I tend to study, radio waves, are like 21 centimeters, about that big. And that goes through just about everything. So it's not blocked out by dust. In fact, 21 centimeters, you can see all the way across the galaxy and far, far away, and through the tree that's sitting in front of your telescope, it doesn't matter. As you move to shorter and shorter wavelengths, then it gets blocked more and more. So by probing different parts of the electromagnetic spectrum, we can see different things in different ways. I'll take questions. Let's see, the first one was there, and then I'll come down here. Yep. Where are the cosmic rays? So cosmic rays are not part of the electromagnetic spectrum because they're particles. But they do sometimes produce, through their interaction, something that we see in other things. Like we'll see gamma rays after a cosmic ray comes in and hits something, and then pops off a high-energy photon. But they're not on the electromagnetic spectrum that way. Yep.
Why is it that radio waves and visible light can penetrate the atmosphere, but the others can't?
Well, not all of them can. So there's a couple of different things that happen in the atmosphere. So visible light comes through the atmosphere, no problem. Ultraviolet gets absorbed by certain molecules. So it interacts, energy is just right so that molecules in the upper atmosphere get excited when that light comes through at those higher wavelengths there. Likewise, X-rays and gamma rays, these very, very small things tend to interact in the atmosphere and don't make their way through. By the time we make it down to visible, it's okay, it gets through, but then there's some parts of the infrared spectrum that get confused by, again, emission from various things in the upper atmosphere. Microwaves come through the atmosphere, no problem, but their wavelengths get wobbled because they're still very high, and radio is your favorite thing because it just comes on through, no problem. Yes? Yes?
From previous slide, I have seen a lot of pictures of nebula.
Yep.
The picture is not a full rectangle, it's like this. The frame of picture.
Yeah. So like this? Yep. So those are the detector chips on the Hubble Space Telescope that are set together like that. So it's like, in your digital camera, you've got a certain number of megapixels, right? You've got one chip, basically, that can see there. They put together multiple different chips in an array, and those things come together and form up these shapes. So there's one chip here and one chip there, and there's another one there. And why they did it that way, I can't remember. Either it got screwed up or it was intentional, and I don't remember. Okay, so what does the galaxy look like in different wavelengths? So I just told you about the electromagnetic spectrum. The image that we saw before was the optical light and the dust, which is blocking it. If we look at 21 centimeters in the radio, we trace atomic hydrogen. I'll tell you about that in just a second. And this is what the disk of the galaxy looks like. Pretty much the same. It's a disk. I mean, we're looking edge on through the galaxy, and it produces this here. The dust is anti-correlated here. So this, where it's dark here, is where it's bright in dust. We're seeing the dust in infrared emission. And in the millimeters, some radio frequencies, we see, so this is like microwaves, we see molecular gas. And again, it's very narrow, tight little disk. So my favorite thing to study is the hydrogen 21 centimeter line. I'm a physicist, so for those of you who are physicists, you'll understand this. We can handle atoms that are very simple. We're not very good at complex things. We like simple things. So you give me a proton and an electron, I can handle that. If you put several atoms together, I get a little bit scared. And I call that chemistry. So I'm a physicist. I like hydrogen because it's really simple. And the hydrogen atom has a beautiful thing called the hyperfine transition, where the electron, which is zipping around the proton at the center, if its spin, so if it's spinning basically like this, is aligned with the proton, it's got one energy state, and if it's anti-aligned, it has another energy state, and they're slightly different. And randomly, about once every 12 million years for a given atom, it flips from the higher energy state to the lower energy state. And when it does, it gives off this really weak photon, which is emitting at 21 centimeters, 1420.40752 megahertz. And that is the hyperfine transition. So I said one atom will flip once every 12 million years. That's a long time to wait. If you're trying to finish your undergraduate degree or your PhD, you don't really want to wait that long. So what you have to do is have a lot of atoms. And you have a lot of atoms, and you see a lot of this emission. You look totally baffled.
Sorry, is that decay rate like a half-life?
It's kind of like that, yes. I mean, it's a spontaneous transition. Similar to a decay rate, you pump up an atom into a slightly higher energy state by banging it with another atom, and it sits in this higher energy state for a really, really, really long time and then spontaneously transitions to it. So most lines of sight through the galaxy, most places where we look through the galaxy, take a place there or there or there, we see 10 to the 20 atoms per square centimeter. So there's a lot of atoms as we look along, and given that many number of atoms, you're bound to have a few of them that are popping over and sending out this very low frequency wavelength. So we get to see the atomic hydrogen line, and it's very bright, actually. You can see it with a little tiny dish that's sitting on top of the School of Physics. Is that dish still sitting on the top of the School of Physics?
It will be with a new building. Yes.
Oh, yes, of course. Yep.
Got a big concrete pad there for put it on.
Excellent.
We're all waiting.
Good. So you can see it very easily with any telescope. So the nice thing about the atomic hydrogen transition, in addition to the fact that it's at 20 centimeters and that's a big long wavelength, is also that it emits at a very, very narrow, what we call spectral line. It's like a radio channel. So you tune your radio to a particular frequency and you get, whatever you want. Classic FM, I'm sure, is what you're all listening to. And you get that station coming in. So you tune your radio receiver to 1420 megahertz, and 1420.405752 megahertz, and you get this very, very narrow burst of emission at this particular frequency. You move off of that frequency, and you don't see it. But if the atom is moving with respect to us, it'll be Doppler shifted. Its frequency gets changed, like a pitch gets changed if it's moving towards you or moving away from you. And so if it's moving away from us, we see the wavelengths stretched out, and if it's moving towards us, we see them compressed. That changes the frequency, and we can translate that into a velocity. So if the gas is moving, we'll see it move away from its rest frequency, and that gives us an indication of the velocity. So that changes astronomy, it's fundamentally two-dimensional science, into a three-dimensional science, because now we can see a little bit more information. Not quite 3 dimensions, it's like 2.5 dimensions. We can see what something looks like on the sky and how it's moving. So that tells us about how clouds change with time, because we can see their velocity structure. So hopefully that answers your question there. Okay, so if we go back to our pretty picture of the Milky Way, and this is what it looks like, in optical, what does it look like if we put on our radio eyes and we look at it in atomic hydrogen? And this is what it looks like if we look at it in atomic hydrogen. So while you look at that, I'll drink some water, and then I'll tell you about it. So this is the whole southern sky in hydrogen gas, as studied in the Milky Way and studied with the Parkes radio telescope. So this is about 2,000 hours of Parkes radio telescope time to create this image, where we have the south celestial pole here and the equator there. The different colors are different velocities. So that's where the gas is moving at a higher or lower velocity with respect to us. Where it's green, or sort of greeny blue, is gas that's quite close to us. And where it's purple and sort of red is gas that's moving quite fast with respect to the sun. Both. So the red stuff is moving away from us, and this purple, no, the purple stuff is moving away from us, and this red stuff is moving towards us. There. And you notice if you look at this, and you look at that, the thing that's really different is all of this. And that is hydrogen gas associated with the Magellanic Clouds. So the Magellanic Clouds are 2 galaxies, dwarf galaxies, that are near to the Milky Way, so the large and the small Magellanic Clouds. You can see them in the night sky. Because they're interacting with the Milky Way is pulling gas off of them. It's much easier to pull gas off than to pull stars off. And so the Milky Way is pulling gas off of the Magellanic Clouds and produces this incredible tail of gas that strips almost all the way around the sky, tracing basically the orbit of the Magellanic Clouds there. But you also see some things that are pretty similar, like the disk structure looks pretty much the same. These little blobs that you see up here, some of them are the initial building blocks of the galaxy, and some of them are nearby galaxies that we can see in their hydrogen gas. So what do we use to make images like that? Well, I said the Parkes 64-meter telescope. This is sort of my instrument of choice because it was my first radio telescope that I went to, and you never get past your first. So the Parkes is my first radio telescope, and I've always loved it. But we use a number of other big radio telescopes, the Green Bank telescope in West Virginia, which is a 100-meter telescope with a really weird-looking structure. You can see here. So it's got an arm that sticks up there. Arecibo, 310-meter telescope. So see, I know the theme is big, so I was trying to give you big things. So these are pretty big telescopes. In optical, they get excited when they get 10 meters. And we're like, 10 meters? Come on. 300 meters, that's what I like. So the Arecibo telescope, the Very Large Array in New Mexico. Radio telescopes often show up in movies. The Parkes dish. We had Arecibo was in a James Bond movie. VLA was in Contact. And the Australia Telescope Compact Array has never been in a movie. But it would like to be. It's feeling sad. So in fact, the data that I showed you where that green image was put together as a sort of composite from this here. So what we're looking at is the data, and each frame in this movie is a single velocity channel. So we're stepping through in velocity through the galaxy where the gas is moving towards us, and then it's going to be moving away from us. And as we move through here, you see it getting brighter and brighter and brighter. That gas is the stuff that's really close to us. That's the local gas, things that are near to the sun. And now we're moving out far away from the solar circle, so away from the orbit of the sun. And you can see the Magellanic Clouds coming up here and the disk of the galaxy disappearing away. And this is the center over there. So if you take each one of these slices of this movie and you give it a different color, you produce that nice green picture that we had before. So what do you do with something like this? I mean, it looks beautiful, right? But we're not here because we like pretty pictures. We're here because we like science, and we want to do something interesting with it. So what do I want to do? Well, I want to understand how galaxies work. And how they work is sort of represented in this diagram. How am I going on time? Okay. Somebody will have to just stop me at some point.
I'll let you know.
Good, thanks. Okay, so how galaxies work is basically this. We have gas. It's sort of hanging out, doing not much of anything, and somehow it gets cold and it collapses into dense molecular clouds. So the atomic hydrogen comes together and forms molecules. Those molecules are colder. The gas gets denser and colder and denser and colder and denser and colder until eventually gravitational collapse takes off and it becomes stars. And those stars have very big, powerful impact on the gas around them. If they're massive stars, they blow a huge wind out where they're throwing off a fraction of a solar mass every year away from the star and pushing gas away at 1,000 kilometers per second. And it forms bubbles in the gas. They act like they're just blowing little bubbles from bubble gum around the stars. And then after this very massive star has blown a bubble around itself, it decides that it wants to be a real pain, and it explodes in a supernova explosion and produces a supernova remnant like this. And eventually that breaks down and goes back into the diffuse gas, and it goes around and around in this circle. But it's not a perfect circle. The galaxy is not a perfect recycler. Because every time a star dies or reaches somewhere towards the end of its life, it forms either a white dwarf or a black hole, and some fraction or a neutron star or some other sort of dead dense object, some fraction of its mass is locked up forever in something that will just sit there getting cooler. Yep, I'll answer that in 2 seconds. So to make up for that, we have to have gas coming in from outside of the galaxy to feed this cycle. And also, these really powerful stellar winds and supernovae that form these two sets of images here can actually blow gas completely out of the disk of the galaxy and get rid of the gas so that it doesn't stay in. So yes?
Does that mean that we'll ultimately run out of gas in order to produce new stars?
Yep.
How long will that take?
Very good question. Should have happened about 7 billion years ago. So we're a little overdue. And the reason for that is that we do continue getting gas, but we don't know where we're getting it from. And in fact, one of the things I'm going to talk about a little bit later is how we think we can get more gas into the galaxy, but we don't see enough of it around to continue getting it. But this is a mystery. You look everywhere in the universe. You look at the rate at which galaxies are forming stars, and you look at how much gas they have in them. And you do the simple sums, they should have run out of gas long ago. So in order to continue their voracious habit of forming stars, they need extra input. Yeah?
With the kind of molecular clouds and nebulae, and you were saying that they form stars and then kind of burst away, does that mean that in X amount of years, like the Horsehead Nebulae and the Eagle Nebulae and things won't exist?
Yep, exactly, yep. So once the stars form, they quite quickly destroy their birthplaces. So they dissociate the molecular gas, and then they drive away the rest of the gas that's there. Yep. Yeah?
What kind of materials does galactic winds contain?
Yeah.
Is galactic winds strong enough to blow up galaxies?
So galactic winds are not terribly strong. They're sort of a little soft kind of wind where they blow out. And most of the material is ionized gas. So it's mostly hydrogen plasma that goes out at about about 1 million to 10 million degrees in temperature. But we think there's also quite a bit of low temperature, that's meaning like 1,000 degrees, gas that's sort of caught up in that. And I'll show you a little bit of that in a few minutes. Okay, so the first thing we're going to talk about is bubbles. So bubbles form around stars. They form from the effects of stellar winds. So the sun has a stellar wind, right? It blows off a little bit of gas all the time. The sun is a low-mass star, and so it doesn't have a very impressive stellar wind. But if we didn't have a magnetic field on Earth, we would feel that stellar wind quite a lot. So it's always blowing off a bit of gas away from it. But more massive stars, stars that are 1,000 times the mass of the sun, they actually blow off a lot of gas. And stuff that is only 10 times the mass of the sun still blows off a lot of gas. So what they do when they blow off gas is they're pushing gas away from them with their winds, that's photons and also electrons and protons. They're pushing away, and they act like a snow plow to drive the gas away from them. And it blows a little bubble like this. So what we get inside is not very much hot gas and a rim around the outside that is that snow that's been packed up together as the snow plow has pushed it away from that. And we see them all throughout the galaxy. They're all over the place. And whenever you see one of these, you can go, aha, there must be a massive star in the center there. And if you ever feel like going onto the Milky Way Project Citizen Science website, you can find bubbles in your spare time. So bubbles around big stars. Stars expel something like 10 to the 38 megajoules of energy over the course of their lifetime. So by comparison, the average Australian household uses about 85 megajoules per year. So we're talking 10 to the 38. It's a lot of energy. An atomic blast is like 10 to the 8, 10 to the 11 megajoules. So we're still a lot much bigger in the stellar winds that come off of stars there.
Question?
Yeah.
Sorry, is that 38 megajoule, 10 to 38 megajoule energy, is that during the course of its lifetime? Or
Yeah.
within the space of what?
No, that's over the course of its lifetime. Yep. So if you blow a bubble around a star. It's kind of tens of light years in size. But if you've got 10 stars, or 20 or 30 massive stars, then they blow even bigger bubbles. And the bigger those bubbles get, eventually they can get so big that they actually exceed the height of the disk of the galaxy. And then they just blow away. And that means that's how they vent. That's how galaxies vent via galactic winds. So now let's talk about galactic winds. And this is an example of something that's a galactic wind, or a galactic outflow. So this is an atomic hydrogen image taken with the Parkes telescope and the Australia Telescope Compact Array. Where it's black, there's very little gas. Where it's orange, there's a lot of gas. And to give you a sense of scale, this thing across here is 1,000 light years in size there. So in order to form something like this, you have to have about 300 massive stars, the 300 stars that are about 10 times the mass of the sun, that have lived their entire lives in this smallish meaning 1,000 light years area, and blown stellar winds and supernovae, putting energy into the gas and driving a big, huge bubble. And it got to be so big that the disk of the Milky Way, which is about this thick here, the thickness of that was exceeded, and it blasted out, much like a mushroom cloud from an atomic bomb. Forms a structure that goes up into the atmosphere because it exceeds the scale height of the atmosphere of the Earth. And so what happens is the very, very hot gas that was in here from those stars goes venting out via these things here that are often called chimneys, and disappears up into the halo. And this is an important process in how galaxies work, because that gas goes up, it's hot, and it cools down, and it comes down in some other part of the galaxy. And it's a way of acting like picking up rain off of the ocean and dropping it inland. So, in a weather system, it might collect quite a lot of water off of the ocean and drop it further inland, and the inland needs that rain. Well, in a galaxy, you need to distribute the gas and the metals and the temperature around as well. And so by having something like this, where you throw hot gas up into the halo and it cools and comes down somewhere else, you can equalize a galaxy so that it doesn't have very different pockets of different types of physical parameters. So as we look around the galaxy, we see different kinds of structures. Which one of these is galactic? That one, obviously, but similar structure. So this is this mushroom cloud effect where you get hot gas that goes venting up and it cools and starts coming back down. And it forms exactly the same sort of structure as the Nevada test site there. And as we look around the galaxy, there's lots of places where these happen. This is actually an artist's impression, so don't believe this one. But there's two places in the galaxy where we see a lot of stuff in the halo. One is over here, and one over here where we don't see as much. We've decided that where we see a lot of star formation, where there's a lot of stars producing a lot of activity, a lot of massive stars, they create a lot of winds, a lot of stuff that they throw up into the halo. And in places where there aren't as many stars, there's not as much stuff in the halo. So this tells us that the halo is directly related to the disk. So back to our cycle of how galaxies work. So we've had our nice pictures of bubbles, and we've had our pictures of galactic winds. What's at the center of the Milky Way? Black hole. Okay. How do we know that there's a black hole at the center? Everything goes around it. Good, excellent. I don't have to give this talk. Okay, so we know there are a lot of stars in the center of the Milky Way. This is an infrared image of the center of the galaxy. The reason it's infrared is that that pierces through the dust that's between us and the center of the galaxy. In infrared, you can see through that dust much further, and you look at the stars in the center. And what you can then do is watch those stars move. And that's what this image over here, oh no. Why doesn't it start? Come on. Okay, well, we won't show that one then. It's not starting. Oh, there it is.
Click it again.
There we go. Okay. So this is from the UCLA Keck group where they've been studying the stars in the center of the galaxy, and they've been mapping out their orbits. So the year is up here. It goes from 1996 or something like that to 2013, and you can see the orbits of the stars here. And based off of those orbits, so measuring how fast those stars are moving around something, whatever that something is, and how far away they are, you can infer what the mass is there. And the inference is that there's something like a 2.6 million solar mass black hole at the center of the Milky Way. And that's puny. That's a tiny little black hole. Yes? What is one solar mass? Sorry, one solar mass is one sun.
What's the scale of that movie
there? That's a very good question. I know what my next one, the scale of my next one is, so maybe we can figure it out from that. But it's on the order of maybe 1,000 AU, something like that, astronomical units there. I have no idea who was next, so I'll just work out from the center. So probably not exactly the same way, because there aren't stars that are more than 1 million solar masses, which is probably why you asked that question. So you can form one black hole, and then you get another star that's right next to it that goes supernova, and the two black holes merge. And then you get another one, and the 3 black holes merge, and you gradually build up the mass until you get up to 1 million solar masses. In the centers of galaxies, where you've got millions of stars in a very small area, lots of things go crazy, and it's a lot easier to merge together multiple black holes, much easier than you would in another part of the galaxy, because the dynamics drive them together there. So the next one was there. Yep.
Why doesn't the black hole just swallow the stars? Why do they orbit around the black hole?
So a black hole has the same kind of gravity as any other object. And its influence on things is just due to its gravity. Right. So if you replace the sun, for example, with a black hole that was the same mass as the sun, other than it being dark and cold, we wouldn't know the difference. Right? It wouldn't suck us in. So the same thing is true in the center of the galaxy. The reason they go around as fast as they do is because there's 1 million solar mass thing that has a lot of gravity associated with it, but it doesn't have any more gravity than that. So as long as the things are outside its event horizon, its area where it really has significant influence and would suck something in, as long as they're outside that, they'll just keep on orbiting around.
Naomi,
yep.
I'm just going to point this, getting up to 5:45. We do need to finish at 6.
Okay.
Now we started a bit late, but I need to point that out.
Yep.
One thing I wanted to say to everyone here is, Naomi's actually going to be joining us tomorrow over at the school for some of the activities there before her talk. So there might be other opportunities. So it might be a good time now to figure out what do we want to do. You want to push on? You want to take some more questions? How should we go?
Let me push on, because there's a couple of things that I want to tell you about that are kind of fun. And then we'll take a bit more questions. So one of them is the very exciting discovery, the Fermi Bubbles. So this made a lot of news a few years ago, about 5 years ago. These Fermi Bubbles are associated with the center of the galaxy. So if you have really big black holes, sometimes you have things called jets. You have, as they're spinning around, when gas falls into them, they spew a bit of highly energetic particles out, and that can form a bubble around it. Or if you've got 1 million stars in a small area, they can form the same sort of bubbles and shells that we were seeing in the other bits of the gas. And in 2010, the Fermi bubbles were discovered with the Fermi Gamma Ray Telescope, showing these enormous big lobes associated with the center of the galaxy, suggesting that something really cool happened in the center of the galaxy some time ago. Now this is the artist's impression of what the Fermi bubbles look like, but they're about, as you can see, about 50,000 light years across. What they actually look like is that, which is not nearly as exciting, but still pretty cool for astronomers. So these are the bubbles here. The center of the galaxy is right in there, and there's these nice, big, bright, high-energy lobes of stuff And for some time, for the past 5 years, we've been trying to figure out what formed them. Are they related to the black hole in the center, or are they related to stars in the center of the galaxy? But one way or another, they give us a neat view into the way that galaxies lose gas via their bubbles. If we zoom in on this area here, and we look at it in atomic hydrogen gas, we see that the hydrogen is missing from the center, mostly missing. So this is where there's a lot of hydrogen around there, and there's virtually nothing in the interior except for this narrow disk there. And we think that's all been blown out by whatever has blown the Fermi bubbles. So it's quite a dramatic area there. Okay, so the last thing I want to talk about is how do you feed galaxies, because there was a question about that, and it is quite a neat thing to talk about. So gas has to come into galaxies. So the Milky Way is a very hungry galaxy. Our star formation rate is something like 1 solar mass, 1 sun per year, is a new star is formed. And if you add up how much mass there is in the galaxy and you form 1 sun per year, you will eventually run out of gas. And we should have run out billions of years ago. But we haven't, and the question is why? And one reason that we haven't is because of things like the Magellanic Clouds. So the large and the small Magellanic Cloud and the stream of gas that comes off behind them that we saw earlier in that sort of green and multicolored image is something that is coming into the galaxy. So that is gas that will gradually be consumed. The Milky Way will cannibalize its neighbors, and that gas can then go on to form new stars within the Milky Way. But if we add that all together, it's not quite enough by like a factor of 100. Yeah?
You stated that the Milky Way forms 1 star per year. Comparing that to other galaxies, is that a small number or a big number? Or?
It's a pretty standard number. There are star-burst galaxies, which form like 10 times as many stars per year. But for a standard spiral galaxy, that's about the same. So we need gas to keep forming stars. We need about a solar mass per year for the past 10 billion years. So where does it come from? Well, it comes from the Magellanic Clouds. It comes from other things called high-velocity clouds. This part is data. This part is artist. This is something called the Smith Cloud, which is about 1 million solar masses of gas coming at high velocity, about 240 kilometers a second, cruising into the galaxy where it's going to impact somewhere about here and form some stars. So that's 1 million stars. But that's not very many in a lifetime of a galaxy. So you need a lot of those. And the real problem is that it's a problem sort of like virga. So does anybody ever know what virga is, other than what the picture shows? So virga is that phenomenon where you're looking out, like this picture, and you can see that it's raining out in the far distance, but that rain never hits the ground. So if you're a farmer out in a dry part, you've probably seen something like this. The rain never hits the ground. You can tell that water was coming down, but it evaporates before it gets there. So it does no good for the ground. The same problem happens in our galaxy as we're getting gas from the circumgalactic medium, from the area around the galaxy. These bits of gas, they're cold bits of gas, come flying in through the halo of our galaxy, and they're traveling at 300 kilometers a second through a medium that's 10 million degrees, and they evaporate. And then they just get left up in the halo and never come down onto the disk. And it doesn't do us any good. We can't form any new stars with that stuff. So how do you get that stuff to hang together long enough to actually make it onto the disk? And the answer is magnetic fields. The answer to all questions in astronomy is magnetic fields. So if you go on to be an astronomer, remember that. You can sit in an audience and you can say, what about magnetic fields? And everybody will think that you know what you're talking about. So magnetic fields provide shields to the gas as it's coming in. And since we are running out of time, I'll just quickly tell you how we know that. So magnetic fields, we detect the rotation. How do I explain this? In 30 seconds, I'm not going to be able to explain it. Trust me. I'm a doctor. magnetic fields can be detected in radio wavelengths by looking at very, very distant sources of radio galaxies, basically. And the way that the polarized light from that changes as it comes through the intervening material. And from that, we can tell that there are magnetic fields, and we can tell how strong they are and in which direction they point. And so each one of these dots here is a measurement of the magnetic field in our Milky Way. Where it's red, it's pointing away, and where it's blue, it's pointing towards us. And the size of the dot tells us how strong it is. And if we look at some of these high-velocity clouds, these things that come flying into our galaxy, like this one here, we can see that all these little dots are blue here, but when we move on the galaxy, they're red. And that's the only thing you need to take away from that image, is that they're different onto this little object here. And that tells us that it has a magnetic field. And it acts like a shield to protect that blob of gas so it can come into the galaxy. So it's just like the Earth's magnetic field is a shield for the solar wind. So the Earth's magnetic field deflects particles, and it provides a nice shield for the Earth. If these high-velocity clouds, something traveling at 300 kilometers a second through the halo of the galaxy, has a magnetic field, it provides a little shield for it. And it can go straight through the halo and bang onto the disk of the galaxy and start forming new stars. So that's my theory. We have to see whether I'm right. And we won't know whether I'm right until we build the next telescope. So this is the next telescope that we're building, and I'm going to tell you about it tomorrow, and I'm going to tell you about its big brother, the Square Kilometer Array, because this is just the little child. This is the Pathfinder. I'll tell you all about it tomorrow, and you can ask me any questions you like, but it'll tell me whether that theory is right and how the Milky Way works. So thank you.